Okay, so now we're going to load in the data. So the data is available to download on the website there. I've saved it on my desktop. You may have saved it wherever else. So just loading the data, the CSV file. I think for me, it's on the desktop. Okay, so, and we're going to call it DAT, okay? And so let's take a look at our data file. Okay, so you can see we've got some information here about each of the studies, all right? So each study has an ID, the name of the author, the year, and some information about the effect size. So as I mentioned before, you might get multiple effect sizes from each paper. And so we have some way of indicating which one it is, all right? So for instance, if we look at this Karim and Wheats paper, there's one effect size related to the Pakistan sample and one related to the France sample. And you can see they have the same study ID because they're both from the same paper. Okay, so study ID, author name. The next thing we have is row. Okay, so this is a correlational meta-analysis. We're looking at the correlation between affect and emotional intelligence. This correlation coefficient has been adjusted, so that's why it's row. It doesn't have to be. We're not going to cover how to adjust or why to adjust. Needless to say that this correlation coefficient has been adjusted for things like the unreliability in the measure. This isn't a problem with a lot of meta-analyses. For instance, if you're comparing two means, right? If you're doing a meta-analysis to see if a drug works and you're comparing the drug versus placebo, you don't have to worry about this. This is mainly to do with correlational meta-analyses, and it's a bit beyond the scope of this first one. Nonetheless, interpret this as a correlation coefficient. All right, so this is the correlation found in each of these studies. N is the sample size, okay, for each of these studies, okay. And we have the branch of emotional intelligence, so total EI, the perception, facilitation, understanding, and management branches. We have the sample. This sample column is actually completely made up. I just made it up for demonstration purposes. I think in the actual paper, they're almost all university samples, I think, from memory or something on those lines. So I've just made this column up to make it a little bit more balanced. And percentage female, again, I just made this up because I was being lazy, really. So these two are made up. The rest is actually, I think, the numbers used from the paper. So we should get similar results to the paper when we do our meta-analysis. Okay, and this is the basic requirements, I guess, of what you need when you're building that spreadsheet. You need a measure of effect size, a sample size, and then any other information you want to do as a moderator, okay? So if you just wanted to do a meta-analysis, all you would want is that effect size and the sample size. Everything else is for moderation, to see if this variable is linked to the effect size. Do we have a bigger effect sizes for total EI versus the perception branch of EI? Do we have bigger effect sizes for studies that have more females? Do we have bigger effect sizes if we look in community samples versus high school samples? So the effect size and the sample size are used to do your meta-analysis, and then all the other variables are used to do meta-regressions or subgroups analysis, which we'll go into in a little bit. The effect size has to be in a consistent format. So whether that's all Cohen's D, if you're comparing two means, R or rho, if you're doing correlations, or it could be a risk ratio if you're doing something like the effect on cancer survival or something like that. So as long as every single row is in a consistent metric, you can meta-analyze it. You can actually meta-analyze anything. It just has to all be consistent in terms of they should be comparable. You're putting them all into the same analysis, they should be comparable. But other than that, you can actually meta-analyze anything. So let's do that. Let's do our first meta-analysis. Okay, so in our data file, you'll notice we have row and n. We need to convert that to an effect size and a variance in the effect size, right? So those are actually the two inputs you need for a meta-analysis. And you can calculate those from this information that we have from row and n. If we were doing a mean differences, we might have mean 1, mean 2, standard deviation 2, and we need to convert those. It's pretty simple for the correlational one. So let's do that. To do that, we use the scal function, all right, effect size calculating function. We have to tell it what kind of effect size data we're giving it. We're giving it a correlation coefficient. And then we need to tell it that which variable in this data set. So which variable in this data set is the correlation coefficient? It's this variable here called rho. All right, so Ri stands for the, R stands for the correlation coefficient of the ith study. All right, so Ri will be this column rho. All right, the other thing we need to give it is the other thing I said we need, which is this sample size. So that is Ni. Okay, so the sample size N of the ith effect size, and that is this column here, and it's just called N. Okay, we need to tell them where to look. So the data is in this data frame up here called DAT. All right. And ES Calc. Okay, so now it seems to run fine this time when I've spelled ES Calc, right? Now if we go back to our data frame, we can see we have these two extra columns, YI and BI. So YI is the effect size for the ith study, and VI is the variance in the effect size for the ith study. All right, so for this effect size here, you can see the effect size is 0.0128, so on, and the variance is 0.006. The variance, how we calculate that is basically 1 over n. All right, so it's the inverse sample size. It's not exactly that. I could show you the exact formula. It's slightly weighted by the effect size, but it's going to be very, very close to 1 divided by the sample size. So bigger, if we look at smaller sample sizes have bigger variance. You should see a correlation between those. Okay, if we look at YI, we can see it is unchanged from rho, okay, because we had already calculated the effect size beforehand, so you can do that with an online web effect size calculator. So this is just added this YI column, which is identical to rho. The nice thing, I guess, is it keeps your code kind of consistent. You'll always kind of refer to the effect size as YI and the variance as VI in your code, and you can reuse that code if you do more and more meta-analysis. But you could ignore this column and just use rho if you wanted to. Okay, so we've computed our effect size. Let's run our first meta-analysis.